Okay, let's get started. Welcome. Thank you for joining my talk about building the matrix. My name is Jan-Peter Sanderman. I've worked with Java for the last 18 years for several large Dutch organizations as a software engineer, software architect, and a technical team lead. Currently, I'm mainly focused on backend software. Currently, I'm the co-owner of a startup called Twigged, and today I'm going to tell you about a project of ours that we finished last year called Beat the Matrix. In that project, we used a lot of hardware, in our case connected to Raspberry Pis and Arduinos. And the focus of this talk will be how to get started on hardware development if you only have a software development background. And by the end of this talk, you can judge for yourself if hardware is hard or not. So let me first tell you something about the project, Beat the Matrix. We built it for a client of ours that runs an activity center. They host activities for all kinds of groups like companies, schools, bachelor parties, and they run from mountain biking and canoeing till pub quiz questions and team building missions. They also have 2 escape rooms that they've built themselves. They're very creative people over there. And the owner came to us and he asked us if we could help him build a new type of game in 10 of his hotel rooms. The game would be themed around the movie The Matrix, hence the title of this talk. Now, Beat the Matrix is a combination of Fort Boyard-like games and an escape room. Teams start in a small cinema where they get to see an introduction and instruction movie. And then they enter a hallway that has doors on both sides, 10 in total. They get an RFID tag, and using the RFID tag they can open a door and enter the room. And in the room there's a game that can be played. And the idea is to collect as many points as possible for each game that you play. Now every game has a time limit of 5 minutes, after which you have to go back into the hallway and into a different room to play a different game. Now 8 groups can play at the same time. And the idea is to get as many points and beat the other groups. Now that's the Fort Boyard part of the game, of the Beat the Matrix game. But as I said, Beat the Matrix is also partly an escape room. In the introduction movie, it is shown that you have to rescue a girl that's trapped inside the Matrix. And you can get her out of the Matrix by giving her a phone call. And in order to try to find her phone number, you have to look for clues in all of the 10 rooms. So let me give you some examples of the games we have in the rooms. There's a room that has 50 push buttons on all the walls. And they can light up in any color. And you have to try to touch only the green ones as fast as possible. In another room, we created a 2x3 meter city out of Lego. And it's a maze, and the ball is running through the maze. And you have to try to touch the phone booth with the ball. Now, the movement of the maze itself is controlled by air pressure. And 4 buttons, left, right, up and down. And each member of the team gets to control 1 button, making working together as a team very important. In another room, we created a classic laser obstacle course. You have to try to get through the room without touching the lasers. It's a simple game, or simple idea, it's only very hard to take a decent picture of it. Then we have a room where you have to shoot targets using a laser gun. But if you're not fast enough, the targets will fire back at you. And there's a room that is filled with magic mirrors, which basically is a computer monitor behind a 2-way mirror that can act both as a monitor and a mirror. And we use it as a gimmick to show pub quiz questions. And the teams can answer the questions by typing a phone number on an old telephone. Now we've also got some virtual reality and augmented reality games, but they will not be part of this talk. So let's look at some differences between Beat the Matrix and a traditional escape room. For a traditional escape room, 1 attendant is needed to monitor the group. And only 1 group can play at a time. And once the group is done playing, the attendant needs time to manually reset the room before the next group can play. All kinds of locks and keys and objects have to be put back in their original position. And if you played an escape room once and you get out, well, it's not fun to play it again. And you can play it only at 1 level. Now, Beat the Matrix is also played in teams, in groups of 3 to 4 persons. But in this case, 8 teams can play at the same time and only 1 attendant is necessary. Each game in each room can be played at 3 difficulty levels. Once you use your RFID tag to open the door, the room knows at which level the game should be played for this group. And you could also play Beat the Matrix a second or third time. in order to try to beat your own score or the score of another team. Now let's say that a team has played game 1 and is back on the hallway. Then another team can play game 1 directly without any manual intervention. Now that's the part where we as Twict came in, to completely automate all the rooms and all the games of the entire Beta Matrix game. And to do that, we've used around 16 Raspberry Pis, 15 Arduinos, 4 PCs, and a lot of off-the-shelf but also custom-made hardware. So we've got a lot of Raspberry Pis computers that need to talk to each other. We run the Raspbian Linux OS on that. We write our software using Java and Python. We use Spring Boot, Py4j to control the GPIO pins that control the hardware. We store our data in a MySQL database. We use REST and MQTT as communication, Angular for the front end, and we created a CI/CD pipeline so that we don't have to provision a lot of computers by hand. It saves us a lot of manual work. But this is business as usual. We do this in our everyday job, so we're not going to talk about this today. But when it comes to hardware, and as I said, we made and combined quite a bit ourselves, there's a lot to learn and discover, especially when you only have a software development background like I did. Are you going to use a Raspberry Pi or an Arduino or something else? And what's the difference? And is it really that easy to get your first LED blinking? Or are there some things that you need to take into account? And how to continue? What if you want to scale up? And what if you run out of GPIO pins and you need more? Let's see if we can get these questions answered today. Let's start with the difference between the Raspberry Pi and Arduino. How many of you own a Raspberry Pi? That's about half the room. And how many also own an Arduino? A little bit less, but not that much. Okay, so well, what's the difference? They're about the same size, and they both have so-called GPIO pins. Pins for general purpose input and output that you can connect hardware to. The biggest difference is that the Raspberry Pi is a microcomputer and the Arduino is a microcontroller. So the Raspberry Pi is more like a computer. You can attach a screen to it, a mouse and a keyboard and a network cable, and it even has Wi-Fi and Bluetooth. And the latest Pi 4B version that I'm using here, that came out this year, has a 1.5 gigahertz processor, and you can get it from 1 to 4 gigabytes of memory. Now the Arduino, on the other hand, is a microcontroller, meant to continuously run one small program at a time. It has a much slower processor, and it has only 2 kilobytes of memory. But unlike the Raspberry Pi, the Arduino also has analog GPIO pins, and is far better at real-time processing. Now, as I said, the Raspberry Pi is more like a computer. So it has a lot of use cases, but just to name a few. You could use it as a desktop PC replacement, and just by changing the software that's on the SD card, you could turn it into a media center that you could put behind your television. Or you could use it as an emulator to play your old Commodore and Nintendo games. Or you could combine a few Raspberry Pis, over 1,000 like Oracle did, and create your own new supercomputer. And of course, you can use it as a means to control hardware, like we did for the Beta Matrix game, but you can also play an acoustic guitar with it. If you want to see more about that, go see the talk by Jago de Vrede on Thursday for that. And of course, last but not least, you can run your entire DevOps presentation on it, as I'm currently doing. Now, on the other hand, the Arduino is a microcontroller, meant to continuously run one small program at a time. It has very little memory, and you have to keep that in mind. Now, as the example shows here, I have 568 bytes left for my local variables. Now, I don't know about you, but that's not the amount of memory I'm used to when working with my Java programs. Okay, let's look at a very simple circuit with just an LED. How to light it up? Well, you need a power source and you need a resistor to make sure that your LED doesn't break. And I know it's a very simple circuit, but still there are some interesting things to take into account. And let's first look at the physical connections, starting with a so-called solderless breadboard. I'm using that to connect the wires, the LED, the resistor, to connect them together. And I can just plug them in and out. And that makes so that I don't have to solder everything together. Now the holes in the breadboard are internally connected, as you can see by the image on the right hand side. So power and ground run from top to bottom on both sides, and the holes in the center are connected together horizontally. So for our simple circuit that I just shown, the components are to get connected together by the orange lines in the picture on the right. And then we have the so-called jumper wires. Now you can get these in different lengths, different colors, and with a male or female connector on either end. Now, since the Raspberry Pi has female headers and the Arduino, let's see, the Raspberry Pi has male headers and the Arduino has female headers, I usually use the wires on the left. They have a female connector on both ends, and you can use a small pin to turn it into a male connector. And you can use these to plug them into the GPIO headers or to the solderless breadboard. Now, let me give you a demo of an LED and a push button and how to make it blink. And before I do that, let me show you the setup I have here. I've got a original Arduino Uno, a Raspberry Pi 4B that's also running this presentation, and a breadboard on which I already connected some LEDs, resistors, push buttons and some wires. Now on top of that, I've placed a Raspberry Pi camera module so that you can see what I'm actually doing here. So now before switching on the camera, let me show you that the Raspberry Linux OS that I installed on the SD card already comes with quite a lot of software. It runs Python 2.7, 3.7, Java. The only extra software I needed to install for this demo was the Arduino IDE. I will come back to that later. So let's fire up the camera. And there we are, live view. Now let me first show you the circuit on the left hand side. So I've already connected the power and the ground of the Arduino to the breadboard, power on one end and ground to the other end. And I've already placed the resistor to make sure that my LED doesn't break. Now I can complete the circuit by placing the LED. Good thing to know, LED shorter leg should be connected to the ground. And you will see that it lights up. Now to show you how the breadboard works, if I place the LED a little bit down, it will still work because the holes are internally connected together. Okay, so I only use the Arduino as a power supply here. It's not running any code yet. Now let's look at the circuit in the middle that also has an extra push button. And the idea is if I press the button, the LED should start blinking, and if I press the button again, the LED should stop blinking. Now to write a program, you need a piece of open source software called the Arduino IDE. So I've already installed it over here, and you need to connect your computer to the Arduino. So I've connected the Raspberry Pi to the Arduino using a USB cable. Now, as you can see, I've connected the LED to pin 8 and the push button to pin 2. Now, a good thing to notice is that the push button is also connected to the power source and the LED is not. So I'm using the push button and the power source to check if the button is pressed, but the LED gets its power from pin 8. Now let's look at the program. Other mouse. The program is called a sketch, and in the top part we define two constants, saying that the LED is on pin 8 and the button is on pin 2. And we define a boolean that keeps track of our blinking state. Are we blinking or aren't we blinking? Now a sketch consists of two parts, a setup part and a loop part. The setup part is run only once during startup or when you reset the Arduino. and the loop part is run continuously. So in the setup part, we define that the LED is used as an output and the button is used as an input. Now the orange functions, pin mode, and there are some more functions here, digital read and delay, they come with the Arduino IDE and they are library functions. You can just use them. Now in the loop part, we check that if the, let's do it like this. If the button is pressed, and then the input value will read high, then we switch the blinking state from true to false or the other way around. Now if we should be blinking, then we turn on and off the LED with a delay of 1000 milliseconds in between. So if I press the button and I move, oh, you can see it. Yeah, you will see that the LED starts blinking every second. Now, just to show you what it takes to make the LED blink faster, let's shorten the delay to 250 milliseconds and then upload it. Now you can see that the Arduino IDE is compiling my sketch. It's being verified and is then uploaded to the Arduino. And it's done. So if I press the button again, you will see that it starts blinking much faster. Okay, so far the circuit in the middle. Now let's look at the circuit on the right hand side. It's the same as the circuit in the middle, also one LED, one push button, but only now it's connected to the Raspberry Pi. So how can we do the same thing? And let's start with doing that in Python. Okay, let me show you. The input button is now connected to pin 23 and the LED is now connected to pin 18. So that's what we define in the top part of the Python file. LED is on pin 18 and the button is on pin 23. Again, we use a boolean to keep track of our blinking state. And in the setup part, we define that we use the LED as an output and the button as an input. Now, if the input button is pressed, meaning that its value is true, we switch the blinking state. And if we should be blinking, we turn on and off the LED every 250 milliseconds. Now, if I run the program and then press the button, it indeed starts blinking every 250 milliseconds. Now, again, let's make that a little bit slower. Run it again. And it now starts blinking every second. No. Okay, so we've seen how it works on the Arduino. We've seen how it works on the Raspberry Pi in Python. Now let's see how it works on the Raspberry Pi using Java. Okay, first thing to notice, the code is a little bit more verbose. I'm using Py4j to control the GPIO pins, and I define my LED pin as a digital output. Then I define my button pin as a digital input. And I again have a boolean to keep my blinking state. And then I add a listener to the button pin. And if I receive a digital state change event, and the event is high, meaning the button is pressed, then I will switch to blinking state. And then in the while loop, if we should be blinking, I turn on and off the LED with a delay of 1000 milliseconds. So let me run that. Compile. And run. And again, if I press the button, it blinks every second. Okay, back to the presentation. seen all this? Okay, so we just made our first LED blink. Well, how hard can it be? Well, as it turns out, it's not that hard. But there are some things that you have to take into account. We already noticed the resistor to prevent our LED from breaking, but let's look at some other things of interest. Starting with the pin numbering. Because we defined in our Python code pin 23 for the input button and pin 18 for the output button. But which pins are those on the Raspberry Pi? Raspberry Pi has 40 pins. Well, as always, it depends. And in this case, it depends on the mode that you set in Python. Now, if you would set it to board, the top one, then you are referring to the GPIO pins by their actual physical pin number, which can range from 1 till 40. Now, in the image on the left, it is shown in the center in the circles that are the actual physical pin numbers. But you could also use the mode BCM. That's what I did. And BCM stands for Broadcom, the manufacturer of the chip. And then you are referring to the pin by their name. And the idea behind this naming is that if the layout of the board would change, you would not need to change your code. So we used BCM, and pin 23, which you can see over here, is on the board physical pin 16, which you could also use if you would set the mode to board. Now, if you run the GPIO readall command on the Raspberry Pi, it will generate this table. In the center, you can see the physical pin numbers running from 1 till 40. The column on the left and the column on the right are labeled BCM, Broadcom. That's what we use from our Python code. The second column and the second last column is labeled WPi, which stands for Wiring Pi. And Wiring Pi is a library that is internally used by the Pi4j library. So, if you're using that, you have to look in that column to get the correct pin number. So to take the button pin as an input, in Python it is pin number 23. Why doesn't it work? Okay, in Python it's pin number 23. And in Java it is GPIO 4, which in both cases is physical pin 16. And in my source code I usually add the physical pin as a source comment. Now, if you want to read more about pin numbering, you can visit any of these links as more background information. Now, as I said, an Arduino has analog pins, and a Raspberry Pi only has digital ones. And the Raspberry Pi uses the voltage on the pin, on the input pin, to determine if its value is high or low. Now, if the voltage is lower than 0.8 volt, it's low. If it's higher than 1.3 volt, it's considered a high input signal. But what if the voltage is somewhere in between? Well, in that case, it's undefined if the Raspberry Pi will see it as a high or low signal. So we want to prevent the pin from floating, as it's called then. And to prevent the pin from floating, you can either use a pull-up or a pull-down resistor. Now, in the circuit I used, I added a pull-down resistor. Let's see how that works. On the website I mentioned here, there's a great explanation of how a pull-down resistor works. And it compares it with a gate. And the gate can open and close very easily, even with a gentle breeze. And you don't know if the gate is open or closed, as it is constantly switching between these two positions. Now, if you would add a spring to the gate, you could keep it closed. And you would need a deliberate push to open it. Now, the gate's position represents the voltage, which is constantly fluctuating. And the spring represents the resistor with which you can use to fix the voltage to either high or low. Now, how does it work schematically? I used a pull-down resistor. And the image on the left-hand side, the button is not pressed. And the input button is connected to the ground through a large, in this case, 10 kilo ohm resistor. But when I press the button, there's a path of less resistance leading to the power source, and then my input pin will read high. Now, the nice thing is you don't actually have to physically build your circuit like this, because the Raspberry Pi has built-in pull-up and pull-down resistors on its GPIO pins. And you can activate it, as I've shown here in my Java code, for a pull-down resistor. Now, the same holds more or less for the Arduino, but it only has built-in pull-up resistors. Now in the Pie4J code, we added a listener to the button pin. And when we press the button, we might actually receive multiple state change events, and that's due to an effect called bouncing. Now bouncing is the effect that two metal contacts in a circuit can generate multiple signals as the contacts close or open. Now we want to prevent that, we only want to have one signal, and Pie4J offers us a debounce option for that. In this case, I've set the debounce to 500 milliseconds, meaning that if I press the button, I will receive a state change event, but then for the next 500 milliseconds, I will not receive any state change events again for the same button. Now, as I mentioned, the first room for Beta Matrix contained 50 push buttons. Now, you can get these buttons online on all kind of arcade stores, but then they light up only in one color. So we modified them slightly and replaced the LED with a RGB LED that can light up in any color. But now I need 4 pins for each button. One for red, one for green, one for blue, and one to check if the button is pressed or not. Now with 50 buttons, that makes a total of 200 pins. And my Raspberry Pi has 40 GPIO pins, but I can only use 28 of them as input or output. The rest is used as a power supply or as a ground. So how to fix that? Well, you could of course add extra Pis and then write your own software to remotely control the pins on the other Pi, or you could use the remote GPIO library that's meant for that. But you could also use extra hardware, and in this case an IO Pi Plus hat. Now a hat is hardware that you attach on top of your Pi. And the IO Pi Plus hat adds an extra 32 GPIO pins to your Raspberry Pi. And the nice thing is that you can actually stack 4 of them together on top of each other, adding a total of 128 extra GPIO pins to your Raspberry Pi. Now, if you want to get started using hardware development, and you don't have a Raspberry Pi or Arduino yet, and this is a nice starter kit. It has an original Arduino Uno, a breadboard, some LEDs, some resistors, some wires, and some other sensors and actuators. And the nice thing about this starter kit is the project book. It explains to you step by step how all the components in the starter kit work. Now, one last thing I want to show you is a piece of hardware that we used in one of the rooms. It's made by Adafruit and it's called the Circuit Playground Express. It's a small piece of hardware. It's a little bit smaller than the Arduino. It's a microcontroller. And it already has a lot of hardware on the board itself. So it has 2 push buttons, 10 pixels, new pixels that can light up in any color. It has a temperature sensor, a light sensor, accelerometer, infrared sender and receiver, and of course the GPIO pins, or actually the holes on the side. You can use them to connect hardware to, but they also act as touch input. Now, the nice thing about this playground is that you can just use it with the Arduino IDE. But the other nice thing is that you could change the bootloader and then run CircuitPython on it. And CircuitPython is Adafruit's branch of MicroPython, meant to continue to directly run Python on your hardware. Now, the editor you need for that is called MU, M-U, I hope I'm pronouncing it correctly, and is also already installed on the Raspberry Pi. So that's it. I hope that by now you have a little bit better understanding of what it takes to get started using hardware development. And if you have any questions, please shoot. Yep.
In which cases did you use an Arduino and in which cases did you use the Raspberry Pi?
Okay, so the question is when did we use an Arduino and in which cases did we use a Raspberry Pi? We mainly use the Arduinos in the part where we needed the extra low-level performance. So, for example, for controlling a large LED strip with hundreds of LEDs on it, then the Raspberry Pi just isn't fast enough to get the signal across to the other ends. And the clock of the Raspberry Pi has too much shift in it to keep the signal steady. So in that cases, we use the Arduino, and we connected the Arduino to the Raspberry Pi in order to stop and start such scripts. One question? Yeah. The question is, if you would add extra pins to your Raspberry Pi, for example, using the head I showed, don't you get an issue with the power of the GPIO pins? Yeah, you do. You have to take this, you have to take that into account. So, from I think the maximum volt, the maximum source that you can draw from your pin is 20 milliamps, but it doesn't scale up. So indeed, you have to take that into account. Yes. No more questions? Oh, one more.
How robust is all the hardware?
How robust is all the hardware? That's a good question. The building that we built this in is actually made completely out of wood. Let's hope it doesn't burn down. But no, it's running now for I think for 14 months right now, and we do a little bit of maintenance. But even the push buttons that get very much aggressive people slamming on it, even they survive that. So it's actually pretty robust. Okay, thank you for your attention.